You're listening to Worth Electronics' What's Up, a radio podcast, and each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast. Today we are finishing our discussion on ferrites, specifically in regards to EMI, or electromagnetic interference. Now, we started this topic last week with Oscar Gonzalez, technical chat navigator at Worth Electronic Online. Oscar recently presented a very popular webinar called EMI 101. And it's important if you are designing any application because you need your electronics to function properly in its environment. In the first half of the presentation, Oscar covered the basics along with an overview of EMI. He also explained the details of chip bead ferrites and then finished with the data sheets associated with them. Today, he finishes with insertion losses and calculations and then wraps it all up with clamp-on ferrites. Enjoy this presentation of the second half of EMI 101 with Oscar Gonzalez.
Next, we will talk about losses. And the reality of life is that in electronics, everything has losses. So the key is to understand what your losses are and control them as best as you can. So, regarding the core's properties, we need to pay close attention to the permeability specifications just to make sure that it will fit in the application. So, every core manufacturer specifies mu prime and mu double prime. Mu prime is the inductive reactance in the frequency range where it is best used as an inductor, and the mu double prime is the resistivity where the part is best used as a filter, because this determines the losses of the core, meaning that it will convert the noise into heat. We can actually deduct the role of each coefficient of the complex permeability based on the impedance formula shown on this screen. We see that the inductive reactance is dependent on mu prime, and the resistivity is dependent on mu double prime. So the same component can be used for either filtering or for inductance, depending on the frequency that it is used. Just so you know, you can refer back to the crossover frequency discussed earlier in order to identify those frequencies. So focusing on the graph shown on this slide, this core material could be used well for an inductor if the frequency of operation is between 1 and 3 megahertz tops. So after 3 megahertz, the mu double prime is very high and the material will have high losses, meaning that it can convert electromagnetic energy into heat. If we identify noise with a frequency higher than 3 megahertz, we could use this material to attenuate it. Now, different materials have a different frequency response. So here we are providing you a guideline for what materials are best suited for what frequencies. So keep in mind this just a guideline based on typical situations. So like with anything else, there are always exceptions, of course. So there are 3 typical materials that we can find for these applications. First of all, we have iron powder, which is the yellow portion of this graph. This is typically used for lower frequencies for noise attenuation because it has the highest core losses at frequencies between 200 kilohertz to 4 megahertz. We also have manganese zinc, which is the red portion of this graph, and it is typically used for frequencies between 3 megahertz and 60 megahertz. And last but not least, we have a nickel zinc, which is the purple portion of this graph. This is used at frequencies of 20 megahertz to 2 gigahertz because it is very resistive at higher frequencies. And so now, if you enjoy performing long mathematical equations, you are going to enjoy this portion of the presentation. But if you do not enjoy performing long mathematical equations, you are going to enjoy this portion of the presentation even more, as I am going to share with you right now some of the tools that we have to make your life easier. So now let's talk about how to do insertion loss calculations and some tips and tricks that you can get to do this easily. So there are a lot of long and difficult mathematical equations to determine how much impedance you need for a component to be within a specific certification for attenuation. And that is represented by the equations here for system attenuation and for impedance. So because of the parasitic properties of the component, it becomes a very difficult and time-consuming mathematical challenge. I will not do a detailed explanation of both formulas, but you can look at them on this slide so you get an idea of the parameters that we need to get into consideration when calculating the impedance needed at a specific frequency to get the attenuation that we are looking for. So the previous image just showed the parameters that we need to consider when doing an insertion loss calculation. This picture right here is a simplified representation of your design. So you have a source and you have a sink. The interaction of your source and sink will cause some noise. So depending on the amount of noise created and at what frequency, this will influence the type of filter that you need. If you have the time and are up to the mathematical challenge, feel free to use the previous equations, or you can use this nomogram you see here. As you can see from the legend below, the typical applications are listed. So we have ground planes, we have supply voltage lines, we have data signal lines, clock, video, USB, and also long data signal cables. The assumed practical system impedance of these applications is shown to the left. So keep in mind that these system impedances values are just approximations and not exact representations for all the applications. But as you will see, for our purposes, the approximation works just fine. And most important, it saves us a lot of time. And most importantly, actually saves us from having to do the painful mathematical equations. So how do you know what type of application to use? Well, you know your board already. You know where the data signal lines are on your board, you know where the ground planes are, and you know where the supply voltage lines are. So again, in this picture, you can see approximated values of impedance for each stage of your circuit. So the ground planes are identified with black arrows, and the supply voltage lines, the supply voltage line is pointed with a red arrow, and you can see the data signal lines pointed with a blue arrow. So every PCB has system impedances associated to it, and this is what CA and CV from the insertion loss calculation equations refer to. Either a source impedance, which is where the interference or emission is coming from, and the load impedance, CV, which is where the interference or emission is traveling to. So what do we mean by system impedances? Well, pretty much the ground plane on a PCB is a large expanse of copper material, and in electrical terms should be 0 volts. To achieve this 0 volts, we need as low resistance as possible, and typically this is 1 to 2 ohms. Next, we have power ports and power lines on the PCB. Once again, we require this to have a low impedance, otherwise we will not have an efficient way of transferring our intended energy around the PCB, and this is why these are typically 10 to 20 ohms. Any external signal cables that connect to your device under tests are likely to have defined impedances. In this case, we have a LAN or Ethernet port. This has an impedance of about 100 ohms. typically these lines have an impedance higher than 90 ohms. So 10 ohms is a really cool approximation. So for this example, we know that we need 12 dB of attenuation at 125 megahertz. We can double check our work with the equation for attenuation below. We just substitute the filter impedance for its actual value, which is 59.6 ohms. And we can confirm that the resulting attenuation is 11.99 dB, the value of attenuation that we need for our power cable at 125 megahertz. So pretty much what we did is that first we just calculated the impedance needed for the attenuation that we need, and then we just confirmed that this impedance value is actually correct. So if you have the same scenario, but this time you use a nomogram, you will find that you quickly come to the same conclusion without doing any mathematical equation. So keep in mind that the frequency is built into the impedance, and therefore you do not have to use the frequency when using a nomogram. You know you need 12 dB of attenuation. You know that it is a power cable with an impedance of 10 ohms. So therefore, you use a solid black line for the supply voltage applications in the nomogram. Follow it until it reaches 12 dB, and you find your result of a 60 ohms impedance requirement. As you can tell, we got pretty much the same result that we got using the mathematical equations, but this way is easier and faster. So just so you know, the nomograms are provided in our catalog and on our website, so you can use them to do the quick estimations for the component you need to pick for your application. So now let's see how our clamp-on ferrites are able to help you with the noise that you might find in your projects. We make our clamp-on ferrites with two different materials. We have a manganese zinc and we have a nickel zinc. This slide provides pretty much a guideline for which material to use depending on which situation you are in. So as I have stated previously, there are always exceptions, but this is what we find to be typical. So to choose the right material, you need to identify first the type of noise that you have in your system. Either it is conducted or it is radiated. So once you identify the type of noise, you can choose the clamp-on ferrite material that you need based on the graph that we have on this slide. So you may use a nickel zinc in situations where you have either conducted or radiated noise. And you can use manganese zinc clamp-on ferrites for pretty much conducted noise. So to choose the right EMC component, it is very important to identify the noise that you have in your system. So first you need to question if you are dealing with common mode noise or differential mode noise. So here's a quick trick to get you heading in the right direction. It is not 100% accurate, but will help you start the process of elimination. So similar to a doctor prescribing antibiotics without knowing if you have a bacterial infection or a virus, he prescribes the antibiotics knowing that if it is a bacterial infection, the medication will work and the problem is solved. If the medication does not work, then at least he knows he's dealing with a virus. So in our case, if you simply apply a clamp-on ferrite onto the cable, both lines, VCC and ground, if the noise is reduced or the immunity is increased, then you know that you're experiencing a common mode problem. But if there is no effect, if there is no attenuation at all, then you have a differential mode problem. So therefore, at the board level, if you have a common mode problem, you could use a common mode choke. If it is a differential mode problem, then you could use a cheap bit ferrite. So here's a visual representation of how a common mode choke works. As you can see in this animation, the red arrow is the differential signal going in, which is the useful signal of your circuit. It creates a magnetic field inside the core going in one direction according to the right-hand rule. And then the differential signal has to go back to the source, which creates another magnetic field according to the right-hand rule. These two signals cancel each other out, so the animated crash is giving you a visual representation of this cancellation. So now, if we talk about common mode noise, common mode signals, we need to understand that both signals are flowing in the same direction, just as we can see in the blue arrows from this image. The common mode noise will create a magnetic flux inside the core that are in the same direction as shown here by the blue arrows. So the core will react to that frequency and convert it into heat. So this is represented by the mushroom cloud in the middle of the core. This fact makes it important that you choose the right core for the specific frequency that you're working with. So, in conclusion, because of the winding structure inside the part, we are not influencing the signal, and therefore, if we choose the correct core based on its complex permeability, and specifically a high resistive portion at the frequencies of the noise, we will get a high attenuation of the noise that we have in our circuit. Now, something to keep in mind when using a common mode filter is that there will be a differential impedance that could attenuate your signal. As shown in the graph above, the blue line represents the common mode impedance, and the red dotted line shows the differential impedance. If your useful signal is at 100 megahertz, for example, and you're using this common mode choke for your solution, you will be unintentionally attenuating your signal. It is important to take a look at both impedances just to make sure that it is good to attenuate the noise and not affect your useful signal. So the next slide will show you a specific example. The blue line right here represents your common mode impedance, and the red dotted line once again shows your differential mode impedance. Your useful signal is the thick black line at 4 megahertz that you can see on the graph. So as you can see, you're making a good use of the common mode choke because it has a high common mode impedance at 4 megahertz and low differential mode impedance. Therefore, the impact on your useful signal is kept to a minimum. The impedance and the upcoming attenuation on your signal is not significant. Our datasheets will show you both the common mode impedance and the differential mode impedance for that part, so you can be aware of the effects that you can expect on your signal. So there are two types of windings in our common mode chokes. We have sectional windings and we have bifillar winding. The sectional winding components are mostly used for power supply applications, but can also be used as an inductor to attenuate differential mode noise. The sectional components have a higher leakage inductance and therefore, just as we discussed before, they attenuate differential mode noise as well as the common mode noise. So bifillar winding parts are typically used for signals, for signal lines because we don't want to attenuate the differential mode signal, meaning your useful signal. So there is a lower leakage inductance that is utilized for filtering noise on a signal. So it is important to know that where the differential mode impedance is and be aware of your differential mode signal. Common mode noise can be solved with a sectional or a bifiller winding part, and the way that it attenuates the noise is very similar. In contrast, there is a big difference if you're using a sectional or a bifiller part to attenuate differential mode noise. You can see these differences as shown with the red and blue lines in this graph. So the sectional winding provides a higher differential mode impedance at any frequency in comparison to the bifiller winding. That's the reason why it is mostly used in power supplies, because we don't worry about any differential mode signal. However, the bifiller winding is good for data lines because we care about our differential mode signal, which should not be attenuated, and its low differential mode impedance helps to keep this attenuation at its minimum. Now, we will take what we just learned about common mode chokes and we will apply it to clamp-on ferrites. So the clamp-on ferrites are typically used as common mode filters. A single cable goes through the ferrite, but the cable includes two wires. It comes with VCC and with ground. So you can also use a clamp-on ferrite as a differential mode filter. But now you must separate your wires in the cable so that you have a single wire going through the ferrite. So the type of clamp-on ferrite you choose will depend upon the intended use that you want to give it. So our clamp-on ferrites are made from two materials. We have manganese zinc and we have a nickel zinc. The blue line right here represents the nickel zinc parts. This is the impedance curve that we can get from this clamp-on ferrite with only one turn. As we can notice, its impedance is actually not very high. So, by adding multiple turns through the ferrite, you are increasing the impedance, but you're shifting the frequency range because you're adding capacitance. So this second curve shows impedance you will get if you do two turns through the clamp-on ferrite. This third curve shows impedance with three turns. So as you can notice, a higher impedance but shifted frequency range. The red line right here represents the same example with the manganese zinc. So here we can see the impedance with only one turn. If we add another turn, we can notice that impedance increases, but the frequency is not shifted drastically. So that is because the manganese zinc is a much narrower bandwidth material. And then now we have three turns through the manganese zinc clamp-on ferrite. Notice that as you add turns with a manganese zinc product, you increase impedance, but the frequency does not shift drastically. So depending on the frequency and the impedance that you need for your application, you will need to choose either a manganese zinc ferrite or a nickel zinc ferrite. Now, this slide shows three different types of clamp-on ferrites that we offer. First, we have the FIX-LFS or low frequency suppression, which is made of manganese zinc and therefore used for low frequency noise attenuation. We also have the Star Tech, the Star Ring, and the Star FX, which are made of nickel zinc to attenuate higher frequency noise. Last but not least, the Star Gap. This is a clamp-on ferrite aimed at the noise above 100 megahertz up to 2.5 gigahertz. So once again, it all depends on the range of frequency where you need to attenuate the noise. So hopefully by this point of the presentation, you have gained an appreciation of designing your products with EMI in mind. So if you do not, well, you can find yourself spending thousands of dollars per visit to the EMC lab trying to fix your problem. Or it can get even worse. I mean, you can find yourself being fined in amounts in the hundreds of thousands of dollars because you're not complying to the EMC regulations required by your industry. So in summary, using relatively inexpensive EMC components at the beginning of your design can show you a big cost savings by the time you ultimately get your product to production. This is a bonus slide that I would like to share to you. We have a lot of tools on our website to help you choose the proper component for your application, as well as direct salespeople and application engineers located all over the world that will be willing to come visit you in person to get the best solution for your EMC problem. I highly recommend you to use our software with Expert to simulate the needs of your system and get the best options available for your design. We have sections dedicated to chip bit ferrites, also common mode chokes for mains power lines and for data lines. We also have a simulator for cable ferrites and more. So feel free to try it and enjoy the benefits that it can get you by selecting a suitable component for your application quickly.
This podcast was taken from a Worth Electronic webinar. To view the materials and replay the webinar on demand, click the link attached in this podcast. As mentioned before, our presenter, Oscar, is a technical chat navigator with Worth Electronic Online. You can chat directly with Oscar and the team by clicking the chat icon at www.we-online.com. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on interesting topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.